Hi class, what we're going to do right now is just go over the second part of the resonance section, review section. You might remember we did this so this isn't the actual class lecture because we were using a different recording program and it didn't work out so well. So this is basically a second go around for me on this part. So what we wanted to do was give you some hints on how to draw resonance structures, and when you're drawing two resonance structures, some tips as to where some common errors happen to be. And so the first tip is in regard to the electronic or the electron bookkeeping with regard to formal charge. So whenever you're drawing resonance structures, the two structures, or three or four, whatever they happen to be, the overall formal charges should be equal when you interconvert between the two. So on this structure on the left here, carbon's got a positive formal charge, oxygen has got a negative formal charge. So total those up, it's neutral. And if we were to move these lone pair electrons down to make a pi bond, the structure on the right, there's no formal charges in this molecule, so its overall charge is neutral. So that's the first step. So if you got the carboxylate anion, here's another example. We are moving the lone pair electrons down to make a pi bond, moving the pi electrons up to make a lone pair, negative formal charge on one side, negative formal charge on the other. So the total charges should be equal between the two resonance structures. So pattern recognition. So you will always be able to draw, I shouldn't say that. One of the most common places you'll be able to draw a resonance structure is in the situation of an allylic lone pair. So what does allylic mean? Allylic is the position beside a double bond. So the two carbons which make up the double bond here, these have got a historical name called vinylic carbons. And the position next door in this molecule, I've drawn carbons here. All of these carbons that are attached to the double bond are allylic carbons. There is a similar situation when you've got an aromatic ring, and the position on the aromatic ring, which is one away here, if we had a carbon atom here, this carbon would be called the benzylic carbon. Benzylic. So it is similar to the allylic. So the rules we have for allylic lone pairs will also work with benzylic lone pairs. So when you've got an atom which has lone pairs in this position, they can be delocalized into the pi bond, into the pi system, where we move these lone pairs down to make a pi bond, and the pi electrons in the double bond become a lone pair. So there's this delocalization, of allylic lone pairs into the pi system. So allylic lone pairs are going to be able to participate in resonance for all of these structures. So for this to take place, I think the next slide shows this. Next slide's talking about the difference between localized and delocalized. So when you've got electrons that can participate in resonance, like such, draw a resonance structure. H, 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 H. We need our formal charges, minus and plus. So allylic lone pairs can be delocalized into the pi system. So we would say that these lone pairs can be delocalized. A lone pair, like which we've got drawn right here, you'll notice that on the carbon next door, there is no pi system. They're all sigma bonds, 1, 2, 3, 4 sigma bonds. And there's no way to move these lone pairs onto this carbon. That's impossible because this carbon's already got 4 bonds, 4 sigma bonds, and it can only have 4. So it would be breaking the octet rule. So the lone pairs here are localized on that nitrogen. Okay, good. That's what. Now, the interesting part, this is what I was going to get to next, is that if you have an atom which can, in the allylic position, which has some lone pairs, and they can be delocalized and draw a resonance structure, the hybridization of this atom has to be, in this case, sp2. And this is really important. So the lone pairs on this nitrogen are in a p orbital. And why do we know this? Because in the resonance structure, we're forming a double bond. And where do you make double bonds? What type of orbitals do you make double bonds with? P orbitals. And so this is one of the few exceptions. When you're looking at a Lewis diagram, you can normally tell the hybridization by just counting the number of sigma bonds or pi bonds, sigma bonds and pi bonds in it. And if you're to just look at nitrogen here, just draw H's, H, lone pair. You might say to yourself, oh, well, this is sp3, but no, it's not. Because these electrons can be delocalized into this pi system, this means that they need to be in a p orbital. And if they're in a p orbital, this will have to be, in this case, sp2 hybridized. Because remember, with resonance structures, it's only the movement of pi electrons and lone pairs. You do not change the shape of the molecule. You do not change any atoms in the molecule. And if you were to go from being sp3 to sp2, you would be changing the shape, which means that this nitrogen, the start, has to be sp2 right from the start. So these lone pairs are in a p orbital. Whereas the lone pairs in a localized nitrogen atom would be in an sp3 hybridized orbital. So this is the important part. Because this nitrogen can make a pi bond over here, pi bond, the resonance structure has to be sp2 because a pi bond requires a p orbital. Excellent. Okay. Next slide. Okay, so just as in the case with if you have in the allylic position, you can have lone pairs. You can also have an empty orbital, in this case, a positive charge. So if you've got a carbon with a positive charge, this carbon is going to be sp2 hybridized, and it is going to have an empty p orbital. And so in this case, the pi electrons in this double bond can move over to make a double bond, and the p orbital on this carbon is now empty. It's got a positive charge. This follows the first little rule. One side starts with a positive charge. The resonance structure on the other side's got a positive charge. And so this positive charge is basically covering the 3 atoms, and these electrons are delocalized over this same system. The only difference is in the previous example, there was 4 electrons being delocalized. In this case, there's only 2. And that's why there's a positive charge on this carbon or a positive charge on this carbon. But this positive charge is basically moving across, right? Good. And I think on the next slide, I have drawn this empty p orbital. And so these electrons are shifting over, pi bond shifts over, and you've got an empty p orbital over here. And yet, as I said here, on the bottom, the situation looks very similar to the allylic lone pair situation, except for one system had the 2 electrons in the allylic position, and in this case, we've got no electrons in the allylic position because it's got a positive charge. And the other difference you will notice is that when the nitrogen had its lone pairs, get your carbon with the p orbitals. So if this is your pi bond here, pi bond, you'll notice that in the allylic lone pair situation, the electrons are moving towards the pi bond, and then these would go over here. In this case, where it's empty, the electrons are moving across to the empty orbital. The electrons are moving across to the empty orbital. So this is following our mantra, negative goes to positive. Empty orbital, the electrons are moving towards that empty orbital. Lone pair, negative, it's moving. It's where the overall this is starting. All right, good. The next pattern recognition is a pi bond between atoms of different electronegativity. So this carbonyl, carbon with an oxygen double bond, this bond, of course, is polarized in this direction because carbon is more electronegative than, because oxygen is more electronegative than carbon. So if you move these pi electrons to become lone pairs, you got a situation like this where the more electronegative atom has got the negative charge, and the more electropositive atom, carbon, has got the positive charge. So it always moves towards the more electronegative atom. So you wouldn't want to have oxygen with a positive charge and carbon with a minus. That would be fundamentally breaking this rule. So keep that in mind. And if you've got a carbon-carbon double bond where there's no difference in electronegativity, you never want to move the electrons from a pi bond to one of the carbons, because what we're going to see later on in the class is that carbocations are high energy, very high energy. Carbanions are high energy. So this would play absolutely have no significance with regard to the true structure. So you can't do, this is a big no-no. So if you've got, this would be the most common mistake in organic chemistry because we're dealing with carbon all the time. So don't make this error. If it's got, if you've got carbon, say, bonded to a nitrogen, sure, nitrogen's more electronegative than carbon, so you can move those electrons there. But atoms with the same electronegativity, don't do that. Okay, so number 4 is very similar to number 3 in the sense that here if we start in number 3, we said, okay, we've got a carbon and an oxygen, they got different electronegativities, and we've got a pi bond between them, so we can do this. And that would generate the resonance structure over here. And so if you've got a lone pair besides a positive charge, these electrons can move down and you will form your pi bond. So in a way, it's a reverse of that. But there are certain situations where you can actually have a carbon with a positive charge and some lone pairs next door, and they can generate a pi system. The nitro group is another example of this. So this was the first group where we were actually doing talking about resonance with. The nitro group is going to be going through this resonance process because really the true form of a nitro group isn't a single bond and a double bond, but really both of these are 1.5 bonds. But you see here, negative charge besides positive charge. So move that down to make a pi bond. But in this case, you can move those electrons away because nitrogen's already got its 4 bonds. And then if you've got a cyclic system and you've got a series of pi bonds within them, you can move these pi bonds around the ring. Benzene, this is benzene. This is the classic example of this. And this is probably the very first molecule in Gen Chem we talked about resonance with. So these bonds are constantly moving around the ring. But in this case, you'll notice that you've got 1, 2, 3 pi bonds, and on this side you got 1, 2, 3 pi bonds. At no stage did we make this. Because this would be fundamentally breaking our rule about carbon has got the same electronegativity as carbon, so we should never, ever, ever do this, making a carbanion and a positive charge like that. So don't do that. All right. We'll have a whole section on aromaticity in Organic 2. That's something to look forward to. And this is a cyclic system, but it's also a cyclic conjugated system. So single bond, double bond, single bond, double bond, single bond, double bond. That's basically conjugation. And when you've got a cyclic system like this, there's resonance structures where you can shift the pi bonds around the ring. Now, the second, I guess, part for this is that, okay, I can draw some resonance structures. Are they good resonance structures or not? And there's, yeah, which ones are significant? Here's some, I got 3 rules here. Hopefully they will help out. Okay, so you want to minimize the charges. Now, this rule, there's a grain of salt associated with it. And I just think back to our friend, the nitro group, which I'll draw right here. It's on this couple slides ago. So this nitrogen is going to be bonded to whatever. You will notice with the nitro group that it has got built-in charges, right? It's got a built-in positive and negative charge. So they're always going to be there. So there's certain instances where you can't do that. But what we're trying to say here is that if you've got a resonance structure where you've got a positive charge and a negative charge, and another resonance structure where you got a +2 and a -2, the resonance structure where it's a plus and a minus is probably far more significant than something which has got these really large formal charges. That was one of the things that we were doing our Lewis structures, where we wanted to minimize our charges. Well, it's very similar with regard to this. So let's look at the carboxylate anion, because this is a good example. So if we look at our rules about carbon and oxygen, they've got a pi bond between them and they've got different electronegativity. So what we could do is we can move these electrons up to make a lone pair, and this would generate negative charge on oxygen, positive charge on carbon, negative charge on oxygen. Then we could say to ourselves, oh, we've got lone pairs beside a positive charge. Let's move these down to make a pi bond. Good. So we've got our pi bond, and then we've got a negative charge on this oxygen here. So if we've got 3 resonance structures, 2 of them have got a formal charge of minus, right? This one's got 2 minuses and a positive. So they all obey the rule in the sense that this is overall charge is minus, this overall charge is minus, and this one's overall charge is minus. But you notice that the middle one has got 3 different charges, whereas the 2 ones on the end have only got 1. So under this rule, this would be the least significant of the 3, and it isn't really going to contribute to the resonance hybrid very much, if at all. So the 2 ones on the end are far better resonance structures than the one on the middle. The one in the middle also, you can also look at this carbon is deficient electronically, right? Hence its positive charge. So that's the first rule. The second rule is that you can have positive charges on electronegative atoms as long as their octet is complete. So here's a couple of examples of oxygen with a positive charge, nitrogen with a positive charge. And in each case, the octet of that heteroatom is complete. So the first example is, so oxygen's beside a positive charge. So let's move those electrons down to here. So both of these are legitimate resonance structures. Overall charge is plus and plus. Oxygen does have a positive charge, but its octet is complete. Same sort of thing with nitrogen down on the bottom. Nitrogen's got a positive charge, but its octet is complete. Now, we notice that this resonance structure for the second one wasn't drawn. So if we just move if we forgot about this arrow, if we erase this arrow here, and we decided to do this, move these electrons up, carbon's got a positive charge. Now, and then the second step, these two electrons here go down, and this would give us this resonance structure. If we were assessing the importance of these resonance structures, the structure, the final structure here is a more important resonance structure because every atom has got a complete octet, whereas here carbon has got an incomplete octet for the second one here. So and this goes back to the previous slide. So this is a more significant resonance structure than the structure down here. And that's why I didn't draw it. Does that make sense? Okay. And here is the third rule, which we brought up before. Avoid at all costs, having resonance structures with with opposite charges on carbon. So allylic lone pair, we delocalize it here, carbon with a minus, and then nitrogen with a positive charge. And if we said to ourselves, oh, look, we could have there's a pi bond between atoms of different electronegativity here. Let's move these back to here. The problem with this resonance structure on the right is that carbon with a positive charge, carbon with a minus charge, super high in energy. It's never going to happen. So avoid this at all costs. All right, so that was the redo of resonance 2. Hopefully it made some sense. All right, I will